Hi. Now we will see groundwater movement. So you just see this figure. It is raining and surface water is moving through the rivers and then it is finally reaching the sea. Just like surface water, groundwater is getting infiltrated and then percolates. It goes vertically as well as horizontally and it joins the sea. This even you can call as submarine discharge. From the subsurface, how much water is getting into the sea. Okay, but how we can understand the groundwater movement? So this is moving, right? Water which is infiltrating, percolating, and then it keeps moving. Same diagram here also, going down and reaching how it is moving below the ground. That only we are going to understand today. So the groundwater movement is first studied by scientist who is called as Darcy. So this law is called as Darcy's law. What he tried is he filled the sand within the cylinder, homogeneous sand he considered and filled it with the sand. And he fixed two piezometer. Why piezometer? Because it is confined. It is between the cylinder. So that means it's a confined environment. Okay. Now he fixed two piezometer within that. Now from one end water is passed, then in other end it is coming out. So that means the groundwater is moving through the porous material and it is coming out. Maybe it is going to sea, like that we can consider. During that time, how much is the water level rise in the piezometer? That is shown here. Okay. Henry Darcy, he understood the water flow through porous material. His equation describes the groundwater flow. So this only Darcy's experiment. Water is applied under pressure through end A through the pipe and discharges at B. Water pressure is measured using piezometer. So this is hydraulic head, flow length, hydraulic gradient. So what is the definition of Darcy's law? If you see the definition, Darcy law states that the rate of flow of water through a porous medium. So generally, groundwater is moving through the pores only. So rate of flow of water through a porous medium is directly proportional to the hydraulic gradient and the cross-sectional area of flow. Okay, and even they particularly insist the discharge is inversely related to the length of the flow path. Now, if you see that as a equation, so rate of flow that can be considered as Q and it is directly proportional. So, proportional to hydraulic gradient. In the previous class, we studied about hydraulic gradient. That is nothing but I and the cross-sectional area. So, we consider the area. Now, the proportionality constant is considered as a proportionality constant is considered as the hydraulic conductivity, which is nothing but K. So now discharge is equal to K into I into A. So This definition clearly gives this equation. So rate of water flow discharge is proportional to hydraulic gradient area and the proportionality constant is K. Now, when the discharge will be high, and even other word, this I just missed it. Inversely related to the length of the flow path. What is the meaning? So, K, I is nothing but dH by dl into A. So if you see K, DH, A, everything directly related to the discharge, whereas length is inversely related to the length of the flow. Now let us understand how this discharge varies. You assume if our K is very high, maybe 50 meter per day, then discharge coming out from the cylinder. If you have a very high K, very high conductivity means even the discharge which is coming out will also be high. And this hydraulic change in head. Here also, if you see now the change in head, if it is too steep between the two wells, here, if the gradient is like this, too steep, then also the discharge will be very high. And if the area of cross section is high, then also discharge will be high. So, in case the distance between the two well, maybe you are assuming the length is too large because water has to pass through all the way and then it has to discharge. In such a case, the discharge will be less. So that is why the discharge is directly proportional to KDHA and inversely as the length increases, the discharge decreases. Okay, but if we consider DH by DL as a whole, okay, so if your K is high and steep gradient, we studied that as a hydraulic gradient. If this is high, area is high, then discharge is also high. Maybe if hydraulic conductivity, if water is passing through the clay, then the hydraulic conductivity will be very low. And your steep is not so deeper. It is slightly steeping. So DH by very, this is also low. And there, for any area of the cross section, even your discharge will be low. So what is the gist of is the discharge, the movement of water through the porous medium depends upon the hydraulic conductivity, whether it is a clay through which it is passing or it is passing through the sand. Okay, so the hydraulic conductivity. And I is nothing but the slope, normal steep or um, deeper steepness. So that also matters whenever we study about the groundwater movement. That is the meaning of this definition. Now, the equation, what we have written here, Q is equal to KIA. Now, if we see here, we are rearranging the equation. Whatever we had, Q is equal to KIA. We rearrange that only written here. Q by A is equal to KI. We know discharge is equal to area into velocity. Now, then what is the velocity discharge from there? Discharge Q by A. So here what is a big V is equal to this A is coming down Q by A. That only written here. So the velocity is discharge by area. This velocity is called as Darcy's velocity and this is known as flux. Flux means flow, okay, which is an apparent velocity. That means apparent, the word meaning apparent is it is a false or illusory velocity. Okay, why this velocity is considered as a false velocity? Here we are seeing why it is considered as a false velocity. This velocity is true, maybe if water is flowing just through the pipe, there is no sand particles. You just see this first pipe, the sand is not filled within this. Just like that, we are allowing the water and water is coming out. In such a case, this velocity is true. But in Darcy's cylinder, when he tried, the water is moving through the pores. Okay, because the cylinder is filled with sand and within that the water is allowed to move. Now, what is missing in this velocity? The pore space, because water in reality, it is passing through between the pores, not just like water flow through pipe. Wherever it is having some pore space between the sand particle, it is moving within that. It is not moving just like that. So the porosity is not considered in this velocity. So this velocity is not a true velocity. It is just a Darcy velocity. Okay, but it is not going straight also. Whenever water has to pass through the sand particles, it will go hit this, then it will pass here. Then again it will hit, it will come. So it is passing through the tortuous path. It is not straight. So the apparent velocity means velocity of water through an aquifer if it were an open conduit, if it is a simple pipe. But the flow does not account for the water molecules actually following a tortuous path, the zigzag path, in and out of the pore spaces. They travel quite a bit farther and faster in reality than the flux would indicate. So that is why this velocity is called as false velocity or apparent velocity. Then how do we account for the true velocity or true path this water is crossing? Okay. So if you see here, actual groundwater velocity is higher than the that determined by Darcy's velocity, because it is called as seepage velocity, because water is seeping through this sand material. It is not just like that passing. So it is called as seeping velocity. Seepage velocity is the true velocity which considers the movement of water between the pore space and account for tortuosity of flow path by including porosity in the calculation. Hence, which velocity is high? The apparent velocity, false velocity is high, or seepage velocity, the real velocity which is passing through the porous material, which is high? The water flow between the porous material is high. Hence, seepage velocity is higher than the apparent velocity. Okay. So, in the flow area, we should consider the porosity, not just a cylinder. Okay. So, finally, the seepage velocity is Darcy velocity by porosity. What is Darcy velocity? Just we have seen here. VD, Q by A. That is Darcy velocity. So the seepage velocity is Darcy velocity, which is accounting for porosity divided by n, which is the real velocity. Okay. Now, let us see the validity of Darcy's law. Okay. So now, Darcy law is valid only for, excuse me, slow movement. That is laminar. The water, if slowly moves, we call that as a laminar flow. Okay. So the type of flow is controlled by the Reynolds number. Suddenly, where this Reynolds number is coming into picture, whenever this is one of the even in fluid mechanics of water resources, for the surface water also, if we wanted to describe the movement of water, laminar or turbulent, we use this dimensionless quantity to describe the flow of water. In surface water, if Reynolds number is less than 2300, the river flow will be called as laminar flow. That is, slowly it is moving. In case 2000 to 4000, 2300 to 4000, it is a transition from slow to fast, it is moving. If the Reynolds number is above 4000, we call that as a turbulent flow, heavy flooding. This is for surface water. Similarly, here also Reynolds number is used to describe the groundwater movement within the pore material. Now, can we tell in case the water is moving between the clay particle? We call that as a laminar flow or turbulent flow? We call that as a laminar flow. Okay, in case we have so many fractures in the rock. Okay, now the groundwater is moving through the fractures. It is below the earth only, but too many fractures are there. Now we call that as a laminar flow or turbulent flow. We call that as a turbulent flow. Okay, so that is the use of this Reynolds number. So this dimensionless quantity is the ratio of inertial forces and viscous force. Now, the utility of the Reynolds number is that we can learn the general nature of the flow with no additional calculation at all, because this dimensionless quantity consider the density, viscosity, diameter of the pipe, and velocity. Here, what is the diameter of pipe? It is a groundwater, right? Suddenly, how can we talk about diameter of pipe? Here, you have sand. Within this sand only, the water is going to move. Okay, so the diameter of pipe means the space between the sand particles. This area, this black area only, the diameter of the pipe. So through that area only the groundwater is passing. Then density, viscosity means properties of the fluid. Because in Darcy law also we have discharge is equal to KIA. K depends upon the aquifer material as well as the fluid. In case you assume the fluid can be water, the fluid can be oil. Sometimes if we are going to study the contaminant, oil is getting contaminated with the groundwater and oil also going to move between the porous material. So hydraulic conductivity accounts for material, whether it is clay or sand, as well as it accounts for the fluid property also. Whether it is water, whether or it is oil. So only these two fluid property. It is not just a water property. It is a fluid which is going to pass through this porous material is also considered in the Reynolds number. Okay. Density means the mass weight of the material. Fluid or how much the oil weight may be while passing or how much is the mass or water. Viscosity means the capability, how fast the thickness or it is not a thickness. It tells about water, you know what maybe the viscosity or it is a oil. The density, viscosity are interrelated. The oil cannot run fast between the sand, whereas water will move fast. So everything is considered in this Reynolds number. Then this V is nothing but we studied two velocity. One is apparent velocity, other one is seepage velocity. Which is the real velocity? Apparent velocity is called as Darcy's velocity and actual velocity is seepage velocity. Which is the real velocity? Seepage velocity is the real velocity where water is seeping through the porous material. So, this Reynolds number considers everything. Density, viscosity, diameter of the pore space through which water is moving and velocity. The pore velocity, seepage velocity is coming into it. Now, for groundwater, what is the Reynolds number value? Okay. So the Reynolds number value for groundwater when it is less than 1. Okay. It is laminar. But even up to 10 also, the Reynolds number value up to 10 is also considered as a Darcy's. See here, experimental tests have shown that for flow regimes with values of Reynolds number up to 10 may still be Darcyan. 1 to 10 can be considered as a Darcyan flow only. If it is more than that, when the groundwater can have Darcy law, I mean Reynolds number more than 1, more than 10, maybe if water, you have a rock, okay, you have big fractures. When the water is going to pass through these fractures, the Reynolds number may be more than 10. That is what given here. Laminar. So up to 1, the groundwater flow is laminar. 1 to 10, it is transition. Okay, but above that, it is turbulent flow. This will occur only in case of fractures. This is the value. So Darcy law is valid for slow viscous flow. Fortunately, groundwater flow cases fall in this category. Then typically any flow with a Reynolds number less than 1 is clearly laminar and it would be valid to apply Darcy's law. But up to 10 also it is still be Darcian only, but it is transition. Maybe sand and then fractures with the pores, then it may go to transition flow, but only fracture, it will go to turbulent flow. And also Darcy considered the aquifer, some of the limitations of the Darcy law. This is the validity. Limitation, Darcy considered the homogeneous material. That is some of the limitations. But in reality, the aquifer will have a heterogeneous material. Now, let us do one problem to understand the Darcy's law. Okay. So, now, you see, we will do this problem. It was observed in a field test that 3 hour 20 minutes was required for a tracer It can be water also, but they are testing the hydraulic conductivity. In the previous video, we have told hydraulic conductivity may be measured from the laboratory method or field method. One of the field method is tracer test, which will help to understand from one place to other place how water is moving. Tracer to travel from one well to another, which is located 20 meter apart, and the difference in their water surface elevation was 0.5 meter. Samples of the aquifer, sample mean the soil or the geology which is present. The geology of the aquifer between the wells indicated a porosity of 15%. Determine the permeability of the aquifer. Permeability means hydraulic conductivity, and seepage velocity and the Reynolds number for the flow, assuming an average grain size of 1 mm and viscosity of 0.008 stroke, that is 1 stroke is equal to 1 centimeter square per second. Check the validity of Darcy law. This problem is given in H.M. Raghunath groundwater book. Now let us do this problem. So now we have to do this. Let us do this problem now. Maybe the color. Let us change the color so that it will be. Okay, let us do one by one. We'll use this. They are asking us to find the permeability, seepage velocity, and Reynolds number. The permeability, let us do permeability. Seepage velocity. And Reynolds number. So the permeability is nothing but hydraulic conductivity. So the hydraulic conductivity formula. So how to find? So here they have given one word, tracer test. So for this tracer test, we have formula for hydraulic conductivity. So we will use that directly. Here we are not explaining, we are not going in depth into it. This is the formula. N L squared by T into H. Okay. Now, what is the N given here? In this problem, N is 15 percentage and length. So, between two wells, it is given. So, 20 meter whole square divided by time is given as 3 hour 20 minute into the head difference. If you see the head difference, it is 0.5 meter. Let us just change this time alone. We'll have it in day maybe 3 hour 20 minutes. So if we just want to convert, maybe the entire thing will convert it into hour. So we know 1 hour is equal to 60 minutes. So we have 20 minutes. So 1 minute means 1 minute is 1 by 60 hour. So 20 into 1 by 60 hour, which is 0.33 hour. So our time is equal to 3 plus 0.33. So here we will write 0.15 into 20 meter square divided by 3.33 hour into 0.5 meter. So now we just convert. Again, this hour also we can convert directly. Okay. If we just convert this hour into day, we will get 864.86 meter per day. This is our hydraulic conductivity. Maybe this hour conversion you can try. So 3.33 hour. We know 1 hour, 1 day is equal to 24 hour. So here you can convert 3.33 into 1 by 24. So all the conversion you can do it. We got 864.86 meter per day as our hydraulic conductivity. Now let us move to next session. Where we need to do seepage velocity. Just now we studied seepage velocity is nothing but Darcy's velocity by porosity. See here. Darcy's velocity by porosity. Now, what is Darcy's velocity? Darcy's velocity is nothing but Vd is equal to Q by A, which is equal to K into I. Now, previously we got our K as 864.86 meter per day into our I. I is nothing but we know dH by dL. So 864.86 into 0.5 divided by 20. So which is equal to 21.62 meter per day. So we got our seepage Darcy velocity. So this is Darcy's velocity. Okay. Now seepage velocity is equal to this 21.62 meter per day by porosity. Porosity is given as 0.15, which is equal to 144.14 meter per day. This is equal to 0.025 centimeter per second. Okay. So now we can check what was our, even we studied what was our actual velocity or Darcy velocity. We have two velocity, Darcy velocity and seepage velocity. Which velocity is high? Seepage velocity is the one which is moving through the pores. That is the actual velocity. Okay. Whereas the Darcy velocity is just like water flowing through the pipe, which is less actually. So you can check here. We studied in the definition, the seepage velocity is always higher than the Darcy's velocity. Here it is proved. Now, what is the next thing we need to find out? They are telling us to find out whether the Darcy law is valid or not. The Darcy law is valid if it is less than 1 or 1 to 10 also the Darcy law is valid, which is the Reynolds number. So now we are going to use Reynolds number formula and let us check whether the Darcy law is valid or not. Reynolds number is seepage velocity into diameter, that is grain size, divided by kinematic viscosity. Okay, so now we know our seepage velocity. Here, in this problem, they are given, assuming an average grain size, kinematic viscosity by density. So directly we are taking this. So they are given 0.008 stoke and one stoke as 1 centimeter. So let us solve this. We will convert the units. That's what we are going to do now. Kinematic viscosity given as 0.008 stoke. They are given unit for stoke also. to convert. 1 stroke is equal to 1 centimeter square per second. So kinematic viscosity is equal to 0.8 divided by second. Now let us substitute in Reynolds number. We got seepage velocity 144.14 meter per day, and the diameter, the pore space is given as 0.001 meter, and then divided by kinematic viscosity. That is, we converted into meter square per day. So that comes under 0.07 meter square per day. Day will get cancelled, meter square, because it is the Reynolds number is dimensionless. So this value comes under 2.06. Now whether it is valid or not, so less than 1 or up to 10 also, the Darcy law is valid. So as the Reynolds number is between 1 and 10, the Darcy law is valid. So now we are done with this. Okay. So now let us do another simple problem, which is very easy. An inclined cylinder of 20 centimeter diameter is filled with saturated sand with K is equal to 10 meter per day, is provided with two piezometers 50 centimeter apart. The opening of two piezometer have elevation heads of, you can see here, the opening of the piezometer have elevation heads of 50 and 30 centimeter from the common datum. You have a common datum, and corresponding water levels in the piezometers are 32 and 26 centimeter. Estimate the flow rate through the cylinder. So this is our cylinder. Okay, they are asking us to find out what is Q. Here itself we will do. So we know discharge is equal to Q is equal to KIA. Okay. So now what is our K filled with the saturated sand? K is given directly 10 meter power, 10 meter per A. I is nothing but dH by dl into A. A is pi r squared. So pi we know. R is, here they have given diameter of the pipe, which is 20 centimeter. So the diameter, then radius is 10 centimeter. That I consider it as 0.1. 0.1 whole square. Okay. Now what is our DH? L we know. The length is 50. We will consider that as 50. That is, it is given as centimeter. So we just take it as meter. 0.5 meter. So we need DH. But directly they have not given the DH. So what we need to do is, now we need to find out DH. First, they have given from the datum. So, water level, piezometric head at A, which is equal to elevation head plus pressure head. From here to here is elevation head. Okay. Here to here is elevation head. Here to here is pressure head. That is the total head we have to know. So at A, it is 30 plus 26, which is nothing but 56. At B, same formula, elevation head plus pressure head. 50 plus 32. 82 centimeter, 82 centimeter. Generally, we tend to minus like this, 32 minus 26. That is not correct. Okay, we need to consider pressure head is from the bottom. So, from the common datum. So, now our DH is equal to 82 minus 56, which is nothing but 26. So, 10 meter per by day into 26 by zero point 0.5 into pi into 0.1 whole square. This is the answer. From here, you can get the uh, discharge of this value. Here you can get 1 meter square. Here it is meter square. You will get in meter cube by day. So hope we studied the Darcy law and how it affects the movement of groundwater flow with respect to hydraulic conductivity or gradient, area, everything we understood. So even we have seen through the cylinder if water is passing. Cylinder means in reality if the water is moving through the pores, how much water can be discharged for the given hydraulic conductivity or I. That was the last problem we solved. Thank you.